Chapter 16, Part 7, acid-base titrations. So a titration is just a process that we use to add an acid to a base or a base to an acid. Typically, we use this as a quantitative analysis technique to figure out the concentration of an unknown. So pretty much your steps are this. You figure out a mass or volume of an unknown acid typically, and you put it in a flask, and you add some indicator that's going to be able to tell you when the reaction is over. Then you add the counterpart, the base or the acid, to it until the reaction is complete, until all of it has reacted. And the indicator is going to tell you when that point has happened. So the point in which all of the acid has reacted is called the equivalence point, and that's where the moles of the acid equals the moles of the base, which is an important component. So what we can do is figure out the concentration of the acid from this, because we can figure out moles of the acid by figuring out the moles of the base, and we know the volume of the acid because that was something we measured at the very beginning. So once you figure out from the base, right, you'd figure out the amount of base you had to add, and you can figure out the moles of base from that. And then those two things are going to be equal. So this is what your setup looks like. You have a burette, which is the long tube thing that has your base, and it is slowly added to your acid until the reaction is complete, until all of the acid has reacted. So a curve, a titration curve, is a plot of pH versus volume. So in these experiments, you measure the pH after certain increments of your base has been added, and the equivalent point is when the amount of acid and amount of base are the same. And it's always going to be found on the curve because you're going to see this huge steep jump in the pH, and it's about the midpoint of this huge jump. So this is what a typical curve will look like. So at the very start, before you've added any NaOH, the pH is 2, right? Because this is acidic, that makes sense. Then as you add base, the pH slowly goes up, and then all of a sudden you see this huge jump. That's that big jump I was talking about. So your equivalence point is about, so wherever this halfway point is, that's your equivalence point. And then if you were to keep adding, then the pH would remain in the basic range. So once you looked at this graph, so at the equivalence point, if you looked at the pH, it was 7 because the thing that we formed was water and NaCl. And we already know that NaCl doesn't hydrolyze. Neither of the components react with water to form anything. So at the end of the day, it's just going to be a neutral solution. Now, if you had something that wasn't a strong acid with a strong base, that would not be the case. But we're going to focus on those types of reactions, a strong acid with a strong base. So we're always going to form a salt that does not hydrolyze. Our equivalence point is always going to be at 7. So what you would want to do is use an indicator that would detect the equivalence point at this pH of 7. So if you look at this chart, this jump happens very quickly from a pH of about 3 to about 11. This is a huge jump. So we need one that can detect it in that range. And there's lots of options you can pick. So here are some different indicators. We want one that kind of fits in this range. Oops, sorry, 11 is there. So our goal would be to pick something that changes at and around the equivalence point. So phenolphthalein is going to change. You could have chosen any other option also. So what would the pH of a solution be if we had 10 milliliters of 0.1 NaOH added to 25 milliliters of 0.1 HCl? So what we want to consider is the reaction between them. So what we want to know is how much HCl is going to react with the NaOH. In order to do that, we have to figure out how many moles of each we have, right? Because essentially, this is the reaction that we're going to care about. The acid and our base are going to react to form our water, and that's the thing we care about. So we want to figure out how many moles of each substance we have that could actually react. So we can do that using our molarity. So for our NaOH, changing the volume to liters, we've got 0.001 moles of NaOH. For our hydrochloric acid, okay, so we've got more HCl than NaOH. So that means NaOH is going to be all used up. So we have enough NaOH to react with 0.001 moles of HCl. And then it's going to be gone. So then we want to figure out, okay, well, how much HCl is going to be left over after this reaction occurs? Okay, so we started out with this amount of HCl. We reacted that much. So we have 0.0015 moles of HCl left over that are just excess. So that's what's going to impact the pH. So now what we want to do is figure out the pH is. So remember, pH is calculated using this. So we know how many moles of my H3O plus or my HCl, but I don't know the concentration. That's how many moles, but how much total volume do I have? Now I have 35 milliliters total because those two things were added together. So my concentration is 0.043. So now I can find my pH. So that makes sense because we added an acid to a base. All of the base was used up in a reaction. There was extra acid left over, so we expect our pH to be in the acidic range. Okay. Okay, so if we were to add excess of hydroxide, that means then all of the H3O plus would be used up, and we would have extra OH. We would work it out pretty much the same way. We would find how much the concentration of the OH is now after all of the ones that has reacted, find the POH, and then the PaOH from there. If we are at the end point where the two things are the exact same, everything is going to react and form water, so the pH is just going to be neutral. So what's the pH of 200 milliliters of 0.5 is added to 250 milliliters of 0.3 acid? So let's figure out the moles of each. So in this case, we have more NaOH, right? So we can react 0.075 of each and get rid of all the HCl. And when we react 0.075 of my NaOH, we've got 0.025 moles excess or left over that's still going to be there. So what would that concentration be? Moles over the volume. So we had 200 milliliters to 250. So now, once we've added them, 450 milliliters or 0.450 liters. So now, since this is our amount of OH, we can find the pOH. And then from there, we can find the pH. So again, does this make sense? Well, the pH is in the basic range, which makes sense because we have extra base that didn't have anything to react and neutralize with, so it's just stuck there excess, contributing to that pH number. All right, and then the last thing is just your list of operational skills, things that make sure you cover, make sure you're comfortable with doing all these calculations before your test.